Hello all, I'm Chandra Thapa from CSIRO Data 61 Australia. Today I'm going to present our work entitled FedDICE, ransomware spread detection in a distributed integrated clinical environment using federated learning and SDN based mitigation. This is a joint work with Kallol, Alberto, Seyit, Vijay and Surya. This is the outline of today's presentation. I'll start by introducing integrated clinical environment, which short form is ICICE, and distributed integrated clinical environment, which short form is DICE. Then I briefly talk about ransomware, centralized learning, federated learning, motivation of FedDICE for ransomware detection, discuss on our research questions of this work, present the security architecture of FedDICE and our experimental results, and finally conclude the talk. ICE is a hospital infrastructure with the Internet of Medical Things and medical cyber-physical systems. As we have a large number of devices to be connected to the hospital infrastructure, the American Society for Testing and Materials, ASTM, standardized the ICE framework for interoperability and is presented in the figure. The infrastructure here we talk is the software-defined networking SDN-based infrastructure. And now what's SDN? So SDN is an emerging architecture that uses the software-based controller to communicate with the underlying hardware infrastructure. This is different than the traditional networks, which uses the dedicated hardware such as routers or switches to control network traffic. Multiple ICE need collaborations, for example, training the machine learning algorithm with more data and performance. Now the question is how to connect them. So in this regard, we proposed to connect these ICs through the supernode. Supernode is connected to the IC via the external interface, and by default, neither the supernode interferes with the decisions made by the local SDN controller, nor it sees, collect or transfer data of the connected IC without data approvals. Now, what are the requirements for the DICE framework? So the requirements are the following. Distributed computing. So computations on the local data are limited within the local IC or hospitals. The second one is the local control. The local network and the SDN policies execution must remain within the ICE or the hospitals. The outsiders, such as supernode, can only facilitate them to route and share models, data, and knowledge for overall benefit. The third one is the collaborative approach. DICE needs a collaborative approach. For example, the participating ICE can share their knowledge on detecting some ransomware to alert or improve the detection capability of other ICE. The final one is the privacy, and basically the data privacy, and is demanded by the regulations and the users. Now, what is ransomware? So it's a type of malware that encrypts our file and block the access until we pay the ransom, right? And 85% of the malware are ransomware, and the ransomware attacks are in increasing trend, as you know. And the example includes WannaCry, Petya, BadRabbit, and the PowerGhost. As we know, the traditional cybersecurity mechanism based on signatures and rule-based static policies are not suitable for detecting new ransomware families that have not been seen before or use encrypted communications. So that's why, to solve this drawback, a vast number of solutions based on machine learning and deep learning have been proposed. So what happens in the centralized learning in this machine learning approach is data are collected to one place, and then the machine learning happens on the repository. So the problem here is the data privacy. For example, data from the ICE is privacy critical. It can contain the patient health data and can expose hospitals' internal ICE networks to the others. So in contrast, in the federated learning, models are sent to the ICE, then trained on their local data, and sent to the server for the aggregations to create a powerful model without sharing any raw data with each other. So far we have some intuitions about the FedDICE. That's a federated integrated DICE, right? So now let's focus on the two main motivation factors. So the first one is network flow dataset and its risks. Our dataset uses the network flow or net flow format of the Cisco. So we have the fields includes start time, source IP, destination IP, total packets, and so on, and this provides a deep network visibility. So the problem here is network data of critical infrastructure such as ICE are sensitive. So adversaries can plan for an efficient attack in the network like denial of service attack and filtering attacks by gathering deep network information from the net flow data. The second one is the distributed computations. DICE can leverage the distributed computations and its advantages such as horizontal scaling of the network elements and the fault tolerance. We investigate and answer the 4 research questions in this work as presented in this slide. Let's go one by one. Let's start with the research question 2. That means this provides the details on how the security architecture of FedDICE for the model development, detection and mitigation of ransomware spreads looks like. The architecture presented here is based on the SDN functionalities and components. So now let's see its main components. So the first one is the manager. Supernode has the manager component and manager a software module to manage the FedDICE. The manager runs as a northbound application and interacts with the Supernode SDN controller through its northbound application programming interface. That means it allows the component of the network to communicate with the higher level components. Second one is evaluation engine, which evaluates the incoming network traffic against the relevant security policies expressions. Following the evaluation, the manager determines the flow rules, which are then conveyed to the enforcer modules. Besides, this modules also maintains a policy database. The another one is agents, as we have 2 agents running on each local SDN controller. The first one is PBSA, is a policy-based security application running on the top of local SDN controller, and firstly it mirrors all the incoming packets in information and formats them for machine learning purposes. So this module also stores the formatted packets information in local repository. The second one, Fed agents, that builds the local anti-malware ML model. So the component enforcer, it enforces the flow rules, and the last one is the central learning node. It's present in the supernode again, and it performs the global aggregation of the local models to form the global model in the federated learning. Now let's put everything together and see how the overall security components work together in FedDICE. So firstly, each local ICE Fed agent regularly trains and updates its anti-ransomware ML model through the federated learning. These models are used as policies in our approach, and in contrast to a static policy which is usually manually updated to detect and mitigate the ransomware spread, the ML model based policy updates automatically through the federated learning. Then it is applied to detect the ransomware spread in the local ICE, and afterward the PBSA enforcer executes the policies to remove the infected devices from the ICE if there is any detection. Let's see the data and models. So we use the clinical environment network traffic dataset, and the data is captured in the PCAP and BiNet flow format. The dataset has both the clean and ransomware generated network traffic information by devices which with an operating system such as Windows and Ubuntu. In our studies, we consider 4 popular ransomware families: WannaCry, Petya, Varadharajan, and PowerGhost. The dataset is generated by considering the sliding windows of net flows to obtain the total of 520 features related to the transmission control protocol, user datagram protocol, address resolution protocol, and flow features. The sliding window can have various time durations such as 5 seconds, 10 seconds, 20 seconds. So in the feature generation process, aggregated features are generated using the last flow information of the sliding window duration, and something like 10 seconds. So this is done to collect a wide variety of both the context features and flow features. There are around 150k samples if we use 10-second windows in our network observation. Now let's see the experimental results under the research question 1. That's the need of the collaborative framework in the ransomware spread detection. Dataset distribution was done based on the table left, and we got the results with the feed-forward neural network based models present in the right table. So based on our results for the feed-forward neural network, logistic regression, and support vector machine, which is not presented here, but overall we observed the following. The first one is for all the models trained on the WannaCry and clean dataset, has shown the good performance on the PowerGhost and the test datasets, but detect only a few samples of Petya and Varadharajan. This is indicated by a high FNR greater than 0.98 for the cases. The second one, for all our models trained on the Power Ghost and clean dataset, has shown the good performance in the WannaCry and test dataset. This is the high FNR for the Petya and the Bad Rabbit. The third one is, for all our models trained on the Petya and the clean datasets, has shown the good performance only on the Bad Rabbit and vice versa. So what's the takeaway message here is, we need the collaboration among the clients hospitals, as one model trained on one ransomware is not effective to detect the other ransomware types in general. Now let's see the experimental results under the research question 3, performance of FedDICE over the centralized learning. So we consider two cases here. So the case 1 is for the IID data distribution. That means each client has a clean and all samples of ransomware that are independently and identically distributed. The total sample size in client is the same. The second case is the non-ID data distribution, and here the distribution of the non-ID data set is due to the label distribution skewness. And then we have the two subcategories, A and B, are based on the number of clients. So A is for the 3 clients and B is for the 4 clients. So if 3 clients, we say case 1A or case 1B, then client 1 has a normal and WannaCry samples. Client 2 has normal and Petya, as well as Bad Rabbit. Client 3 has a normal and the Power Ghost samples. So the key takeaway message for both the IID setup and non-IID setup is the following. So federated learning is effective in ransomware spread detection. Its performance is similar to the centralized learning, and sometimes it's even better. For example, the fit for one neural network in federated learning. So this suggests that we no longer need to compromise the data privacy by using the centralized learning. This is the overall results in the bar diagram, how it looks like. Now let's see the overhead time. So as per expectations, federated learning has higher overhead time for the model training and testing than the centralized counterpart. So this can be considered as a trade-off to the data privacy and distributed computations. It is known that the overhead depends on the number of clients and data samples in the client. So smaller data and higher clients can reduce the overhead in the federated learning. Finally, it's time for the research question 4, that's mitigation of the ransomware spread. So in this regard, we presented a policy-based mitigation techniques. For experimentations, we create a small SDN network simulating FedDICE to test our proposed security architecture. For simulation simplicity, we represent the hierarchy of controllers using the SDN data plane devices, where every single data plane device hosts and federated learning module. Our network setup has used the 4 mininet simulated host, that's the clients, connected to an ONOS SDN controller. So in addition, we have taped one Raspberry Pi virtual machines as one of the hosts in the network. We consider this as an IoT devices connected to hospital network. We use a previously recorded set of WannaCry packet traces for the simulation purposes. So together with the PBS agent running in the local ICE, the Fed agent can automatically force the policies and install them in the local controller. Also, the federated learning model gets updated in the regular intervals from the centralized learning node located in the supernode, so allowing the other lead SDN controller to be aware of the learning model changes. The model detects the attacks and the infected data source was removed from the network by the local SDN controller. In this paper, we presented FedDICE, demonstrated its effectiveness, and implemented a policy-based mitigation technique. So studying a large-scale DICE with the large number of ransomware families and adversarial federated learning and ransomware spread detection are left as a future works. So this concludes my presentation, and I'd like to thank you for your attention.